preparing for a defense electronics engineering interview. You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like and share, and drop a topic request in the comments. Question 1. How do you approach designing electronics for harsh defense environments? Defense electronics are designed for reliability under stress, not just nominal performance. I start by defining the mission profile: temperature, vibration, shock, humidity, altitude, EMI, power quality, and service life. Then I choose qualified components, derate voltage and temperature, protect inputs, and design for testability. I also plan environmental screening and margins early. The best design is one that still works when tolerances, aging, and field conditions stack against it. While answering, focus on mission profile, ruggedization, component derating, environmental stresses, EMI exposure, maintainability, and qualification planning. Show that defense design prioritizes predictable operation across worst-case conditions, not only lab performance. Question 2. What steps would you take to reduce EMI and ensure EMC compliance in a defense electronics design? EMC control starts at architecture, not at the test lab. I separate noisy and sensitive sections, define return paths, use solid reference planes, filter external interfaces, and bond shields correctly. For switching supplies, I control loop area and edge rates. I also leave options for ferrites, common mode chokes, and enclosure grounding. If a design fails MIL-STD-461 late, fixes become expensive, so I design with compliance margins from the beginning. Make sure to cover grounding, shielding, filtering, return paths, layout partitioning, cable interfaces, switching noise, and compliance testing. Explain EMI prevention as a design discipline rather than a late-stage troubleshooting activity. Question 3. How would you analyze and improve the sensitivity of a radar or RF receiver? Receiver sensitivity is mainly limited by noise figure, bandwidth, gain distribution, and required SNR. I would build a link budget starting from antenna gain and path loss, then calculate minimum detectable signal using thermal noise plus receiver noise figure. The LNA placement is critical because early-stage loss directly hurts sensitivity. I also check dynamic range, blockers, and ADC headroom because a very sensitive receiver is useless if it saturates in a dense RF environment. In your answer, talk about minimum detectable signal, noise figure, bandwidth, gain stages, antenna gain, path loss, dynamic range, ADC limits, and why sensitivity must be balanced against saturation risk. Question 4. What is the significance of MIL-STD-810 and MIL-STD-461 in defense electronics? MIL standards translate field expectations into measurable tests. MIL-STD-810 covers environmental conditions like vibration, shock, temperature, humidity, and altitude, while MIL-STD-461 focuses on electromagnetic emissions and susceptibility. I do not treat them as paperwork. I use them to drive design margins, mounting strategy, filtering, connector selection, and test plans. A strong answer is to map each requirement to a design decision and a verification method. Be sure to mention the purpose of MIL-STD-810 and MIL-STD-461, how requirements influence design choices, and how verification planning connects environmental, electromagnetic, mechanical, and reliability expectations. Question 5. How would you design a reliable power supply for a mission-critical defense electronics unit? For a defense power supply, I first define input transients, hold-up time, load steps, efficiency, thermal limits, and conducted emissions. Then I pick topology, buck, boost, flyback, or isolated DC-DC, depending on voltage and safety needs. Protection matters: inrush limiting, reverse polarity, surge suppression, current limiting, and under-voltage lockout. I also validate stability across temperature and component tolerances. Clean power is essential because it affects RF, digital timing, and mission reliability. While answering, focus on input transients, regulation, isolation, protection circuits, efficiency, thermal behavior, conducted emissions, stability, and derating. Show awareness that power integrity impacts every subsystem. Question 6. What are the key considerations when designing a high-speed PCB for defense applications? High-speed PCB design is really controlled electromagnetic design. I route critical traces with controlled impedance, continuous return paths, length matching where timing requires it, and minimal stubs. I place decoupling close to IC power pins and separate analog, RF, and noisy switching regions carefully. Vias, connectors, and layer transitions need attention because discontinuities create reflections. Before release, I review stack-up, impedance coupons, crosstalk, eye diagrams, and manufacturability with the board house. Make sure to cover controlled impedance, return paths, stack-up, decoupling, differential pairs, via effects, crosstalk, segregation of RF, analog and digital sections, and manufacturing constraints. Question 7. Explain how you would create an RF link budget for a secure defense communication system. A link budget is the accounting sheet for RF performance. I include transmit power, antenna gains, cable losses, path loss, polarization mismatch, receiver noise figure, bandwidth, required SNR, and fade margin. In defense systems, I also consider mobility, terrain, interference, and environmental losses. The output tells me whether the link closes with margin. If it does not, I can improve antennas, reduce bandwidth, lower losses, increase power, or use a more robust waveform. In your answer, include transmit power, antenna gains, cable losses, path loss, receiver sensitivity, noise figure, SNR, fade margin, terrain effects, and what to adjust if margin is insufficient. Question 8. When would you choose an FPGA over a microcontroller or DSP in a defense electronics system? I choose FPGA when the problem needs deterministic parallel processing, high-rate ADC capture, radar pulse processing, custom interfaces, or low-latency control. A DSP or microcontroller is better for sequential logic, control loops, configuration, and algorithms that change often. FPGAs give timing precision and throughput, but they cost more effort in verification. In many defense designs, I pair them: FPGA for real-time data paths, processor for orchestration, diagnostics, and communications. Be sure to compare determinism, latency, parallelism, throughput, power, development effort, verification complexity, reconfigurability, and typical use cases such as radar processing, motor control, and protocol handling. Question 9. How do you design fault tolerance and redundancy into defense electronics without overcomplicating the system? Fault tolerance starts with deciding what failures the system must survive. I look at single points of failure, critical signals, power rails, thermal hotspots, and communication paths. Then I add redundancy where it matters: dual supplies, watchdogs, health monitoring, graceful degradation, and fail-safe states. I avoid blind duplication because it adds cost, weight, and complexity. The goal is not zero failure. It is controlled behavior when failure happens. While answering, focus on single points of failure, watchdogs, redundant power, health monitoring, fail-safe states, graceful degradation, FMEA thinking, and the trade-off between reliability, weight, cost, and complexity. Question 10. What security considerations matter when designing embedded communication electronics for defense use? Secure communication is built in layers. I would protect confidentiality with approved encryption, integrity with authentication or message authentication codes, and availability with anti-interference design and robust protocols. Key management is usually the hard part, so I avoid hard-coded secrets and support secure provisioning and rotation. I also validate random number generation, firmware authenticity, and tamper response. Security should not be bolted on after RF and embedded design are finished. Make sure to cover confidentiality, integrity, authentication, key management, secure boot, firmware updates, anti-tamper considerations, protocol robustness, and why security must be integrated from architecture onward. Question 11. How do you select an ADC or DAC for radar, EW, or sensor signal processing hardware? I select ADCs and DACs from the signal chain backward. For an ADC, I check sampling rate, input bandwidth, resolution, ENOB, SNR, SFDR, aperture jitter, input range, and interface speed. For RF or radar, jitter and spurious performance often matter more than headline bits. I also consider clock quality, anti-alias filtering, reference stability, and calibration. A converter is only as good as the layout, grounding, and clocking around it. In your answer, talk about sampling rate, resolution, ENOB, SNR, SFDR, jitter, input bandwidth, anti-alias filters, reference stability, interfaces, and how clocking and layout affect converter performance. Question 12. How would you handle thermal management in a compact sealed defense electronics enclosure? Thermal design begins with a power map. I estimate dissipation per component, define ambient and enclosure conditions, then create conduction pads through copper, thermal vias, heat spreaders, chassis contact, or forced air if allowed. I derate components because high temperature accelerates aging and reduces reliability. For validation, I use simulation, thermocouples, and worst-case load testing. In compact defense hardware, thermal and mechanical design must be solved together. Be sure to mention power dissipation, ambient conditions, conduction paths, airflow constraints, thermal vias, heat sinking, derating, simulation, measurement, and the reliability impact of sustained high temperature. Question 13. How would you detect and mitigate jamming or strong interference in a defense communication receiver? Jamming mitigation starts by recognizing the interference type, not guessing. I would monitor RSSI, spectrum occupancy, packet errors, timing behavior, and receiver saturation. Defensive options include filtering, adaptive gain control, spread spectrum techniques, frequency agility, directional antennas, coding, interleaving, and protocol-level retries. The trade-off is complexity, latency, and spectrum coordination. I would also log interference signatures so operators can distinguish equipment faults from a contested electromagnetic environment. While answering, focus on interference detection, receiver saturation, filtering, adaptive gain, spread spectrum, frequency agility, directional antennas, coding, logging, and operational trade-offs like latency and spectrum coordination. Question 14. How do you plan qualification testing for a newly developed defense electronics module? My qualification plan starts with requirements traceability. Each electrical, environmental, EMC, and reliability requirement needs a verification method: inspection, analysis, demonstration, or test. I prefer early pre-compliance testing because discovering emissions or vibration issues after final assembly is painful. The plan should define test setup, limits, instrumentation, calibration, sample size, and pass-fail criteria. Good qualification is disciplined evidence, not a last-minute certificate chase for stakeholders. Make sure to cover requirements traceability, test methods, pre-compliance, instrumentation, calibration, sample selection, pass-fail criteria, environmental and EMC testing, and the difference between verification and informal debugging. Question 15. A field unit shows intermittent failures during operation. How would you investigate and root cause the issue? For intermittent failures, I avoid changing parts randomly. I first reproduce the operating context: temperature, vibration, supply variation, cable movement, software state, and RF environment. Then I instrument the system with logs, scopes, logic analyzers, boundary scan, or built-in self-test. I look for correlations and isolate by swapping controlled modules. The key is preserving evidence. Once a unit is disturbed, the original failure mechanism may disappear. In your answer, discuss reproducibility, field conditions, instrumentation, logs, thermal and vibration triggers, controlled module swapping, failure isolation, evidence preservation, and avoiding random fixes that mask root cause. If you are still with us, congratulations! You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.